welcome. In today's lecture, we will be covering Chapter 12, where we will discuss two functional groups, alcohols and phenols. An alcohol is a functional group that is an OH bond. So any molecule that contains an OH functional group, a couple examples here are ethanol and cyclopentanol, is an alcohol. Alcohols are extremely popular and prevalent in natural products, and they engage in hydrogen bonding, which is a really important interaction when we have small molecules that are interacting with biological systems. For example, enzymes or proteins are often interacting with molecules through a hydrogen bond, through a small molecule, through the alcohol moiety in this small molecule. So here we have a few examples of alcohols that are common in natural products, hydroxyl groups that are common in natural products. In Grandisol, there's an ethyl alcohol, a steroid compound here, cholesterol, has an alcohol in it. This molecule plays a vital role in the biosynthesis of many steroids. It's a precursor to many of these steroids. And so in today's lecture, we're going to go through the synthesis of alcohols. How do we make alcohols from different starting materials? And then we're going to look at some of the chemistry that an alcohol can undergo as a starting material itself. And we're going to go through the naming conventions of alcohols and some of the properties of alcohols. A phenol is an alcohol that is attached to a benzene ring. So this is still an alcohol functional group, but it's more specifically, we can call any alcohol that's attached directly to a benzene ring, we can call those phenols. And a phenol is going to have a little bit different chemical properties than an alcohol. For example, the pKa is different, etc. But it's also a really common moiety that we will find in many drug molecules and many other natural products. Here's just a few examples. Some of them I'm sure you're familiar with, like dopamine. It's a neurotransmitter that's deficient in Parkinson's disease, and it's also commonly released as an endorphin, like while doing activities such as running. Capsaicin, the molecule that is responsible for spice, has a phenol. Uh, THC, the proactive drug found in marijuana, has a phenol on it. So to begin with, we'll just look at the naming convention. Um, Naming convention is going to be similar to the naming convention we looked at for other functional groups. Most importantly, we're looking at the ending. Uh, we're going to be using an alcohol OL at the end. So to begin with, we identify the parent chain. That's what we've done to name all of the organic molecules we've looked at. And then we identify and name the substituents. And then when we assign the location, this is the biggest difference. When we assign the location of each substituent, we want to make sure that we give the carbon that the alcohol is attached to the lowest number possible. So instead of just trying to assign any substituent to the lowest number possible, for an alcohol, we're specifically looking for the OH, and that's what we want to assign to the lowest number possible. Then we're going to list the numbered substituents in alphabetical order and put the OH location either just before the parent name or just before the OL suffix. So let's look at an example of this. So for this molecule, we'll begin by identifying the parent chain. So we have, for example, pentane. The parent chain would be 5 carbons, so we would have pentanol, right? It's just on the 1 position. We have 1, 2, 3, 4, 5 carbons, and that will be pentanol. We replace the E of the alkane ending ane with OL, E with OL, so we have pentanol. On this next example, we have an 8-carbon chain as our parent chain, so this would be 1, 2, 3, 4 methyl octane. And if we replace that with an alcohol here, now we have to figure out what the parent chain is. And we identified that in this molecule, the parent chain was 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. But now we have a situation where the alcohol is not part of the longest chain. So the alcohol is going to take priority. So our new parent chain must include the connection to the alcohol. So in this molecule, our parent chain is going to be 1, 2, 3, 4, 5, 6 carbons. So we'll have a hexanol. So once we've identified the parent chain, we're going to assign a location to each substituent. So here, we can start from one of two sides. 1, 2. This would, starting from this side, would put the alcohol in the second position. And if we started from this side, 1, 2, 3, 4, 5, 6, it would put the alcohol in the sixth position. So we want to make sure that we give the carbon that the alcohol is attached to the lowest number possible between the two choices. So the correct format will be to have the alcohol in the second position. Then it would put the dimethyl in the fifth position and the alkene in the sixth position. And then finally, we have two options of where to put the location of the OH in the alcohol. We can put the OH in the name. We can put it in the beginning, so that would be before the parent name, so 3-pentanol, or we can put it between the OL, so pentane 3-ol. Both of these would be correct. For alcohols that are attached to OHs that are attached to a ring, we're always going to prioritize them as number 1. So if we just have a simple cyclopentanol, that would be also cyclopentane 1-ol. In this example, we have three substituents. We have a dimethyl in one position and an OH in the other position. And so we also have stereochemistry on the OH. So this would be R. The stereochemistry for the OH would be R. And then it would be 3,3-dimethyl cyclopentanol. And since the OH is in the one position, we actually don't have to include the number in the name. We also have some common name for some alcohols. So we have 2-propanol, that would be isopropyl alcohol. Tert-butyl alcohol, that would be 2-methyl-2-propanol. And then also benzyl alcohol would be instead of phenol, don't get this confused with phenol. It's close to phenol, but there's an extra carbon, right? So this OH is attached to an sp3 carbon. In phenol, we're attached directly to the benzene ring, and that would be an sp2 carbon that it's attached to. Similar to alkyl halides and carbocations, we're going to classify the alcohol based on the type of carbon that it's attached to. So the carbon that the OH is directly attached to, or alpha to the alcohol, depending on how many carbons are attached to that, it'll either be a primary, secondary, or tertiary alcohol. So if there's one R group attached next door and 2 hydrogens, that'll be a primary alcohol. If there's 2 R groups and 1 hydrogen, and an R group is any carbon group, that would be a secondary alcohol. And if there are 3 R groups, or 3 carbons attached to the alpha carbon, that's a tertiary alcohol. When we have a phenol, or an OH group that is attached to the benzene ring, the parent name will be phenol. So, for example, this compound. The OH is taking priority, so that'll be the 1 position. The nitro would then be the 2 position, and the chlorine would be the 3. So we have 4-chloro, 2-nitrophenol. So here are some examples, and you can try to work on naming these on your own, but we will go through some of them during the lecture meetings. There are a few alcohols, and these are the lowest molecular weight alcohols, that are extremely important in industry, um, with with billions of gallons of them being produced and used each year. So methanol is the simplest of the alcohols, and it's just one carbon, one methyl group attached to the OH. 2 billion gallons of methanol are made from carbon dioxide and hydrogen gas every year. Methanol itself is actually poisonous, but it has many uses. It's a great solvent. You can convert it into other molecules, or you can burn it as a fuel. And so you do want to be careful because methanol is poisonous, and it's often used in the lab for, like, you can even use it as for cleaning. It's really good at dissolving, and so you just want to be careful when you're using it because it does convert to formaldehyde in your body, and formaldehyde itself is poisonous and will lead to going blind. Interestingly enough, if you ever uh, are have methanol poisoning, or you know somebody who has methanol poisoning, the cure to methanol poisoning is ethanol. So ethanol is produced by the fermentation of grains and fruits, and it's made industrially within the acid catalyzed hydration of ethylene. So we go through 5 billion gallons a year just in the US of ethanol. And it's got several uses as a solvent, as a precursor for chemical syntheses and fuel, which are all similar to methanol, and human consumption. So ethanol is suitable for drinking and heavily taxed. Now, one interesting thing is that the laboratory grade ethanol is often denatured or includes some sort of contaminant that doesn't allow it to be consumed. So, if you ever get the funny idea to take lab ethanol and try to drink it, you're potentially going to poison yourself. So definitely do not do that. And then finally, isopropanol, 1 extra carbon. Isopropanol, or rubbing alcohol, is often used as an antiseptic. It's made industrially from the acid catalyzed hydration of propylene. So a brief discussion of the physical properties of alcohols. We can compare the boiling points to alkyl halides as well as alkanes. Um, it boils at a much higher temperature, and this makes it a much better solvent. And the reason it boils at a much higher temperature is because alcohols can undergo hydrogen bonding. And so we can have a Lewis base or a lone pair electron forming a partial bond, a weak bond, with the proton shell, the partially positive proton shell. Remember, the difference in electronegativity between hydrogen and oxygen is extremely high. So there's going to be a partial positive charge on the hydrogen, and this will allow it to be attracted to anything that has a negative charge. So any alcohol with 3 carbons or less is miscible in water. Miscible means that they'll kind of dissolve together and form just one phase, water and whatever alcohol. And in general, alcohols will have 2 regions. They'll have the hydrophobic region, that's the alkyl region, the alkane region, and they have the OH region, which is the hydrophilic region. That's what's going to be hydrogen bonding to, for example, water or some other hydrogen bond capable molecule. The longer the carbon chain, or the more carbons we add, then the smaller percentage of the molecule is this hydrophilic region. And so the longer the carbon chain, the less likely it's going to be able to dissolve or mix readily with water or be miscible with water. An alcohol can be used as an antibacterial or an antifungal agent, and this property depends strictly on the alkyl chain length. So you can see here on this graph the potency of how well it acts as an antibacterial or antifungal has a sweet spot between an alkyl chain length of 6 and 10, where it's most effective. And this is because the alcohol needs to have some water solubility to travel through the aqueous media. So you need those OH groups forming their hydrogen bonds. But to be a potent antibacterium, once it's in the media, right, it's going to have to then go through the membranes, and so it needs a hydrophobic region to be able to travel through those membranes. So here's an example, hexyl resorcinol, and this is a good example of this type of compound. It has an alkyl chain length of 6. So since we have this OH group, we've got a hydrogen that is attached to a heteroatom, which means that this hydrogen is going to be acidic. And so in order for us to deprotonate any alcohol, we're going to need some sort of base. So the next few slides are going to be going through some of the acid-base chemistry of alcohols. So we have ethanol and the conjugate base of ethanol, which would be sodium methoxide. There are a large number of bases that are capable of deprotonating ethanol. The most commonly used are sodium, potassium, and lithium metals, and sodium hydride. So in the example of sodium hydride, the lone pair from the hydride is going to act as a Lewis base, form a new hydrogen-hydrogen bond. While breaking the hydrogen-oxygen bond, the electrons from the hydrogen-oxygen bond are going to go to the oxygen, which leaves 3 lone pairs on the oxygen and a negative charge, and hydrogen gas as the byproduct of the reaction. So if you perform this reaction, you would see hydrogen gas begin to bubble off the reaction media. 3 metals, sodium, potassium, and lithium, can also be used, and they also form hydrogen gas as a byproduct. So a little bit of review from the acidity chapter. In order for us to look at the acidity of the compound, we can compare it directly to the stability of the conjugate base. So for a alkane, we have a very low acidity, which means that also the deprotonated version, an anion, a negative charge on carbon is not very stable. As we increase the electronegativity of what the negative charge is attached to, we're going to be able to increase the acidity. So amines are going to have a pKa between 35 and 40, and then alcohols are going to have a pKa between 15 and 18. And then finally, our halogens will have the pKa between negative 10 and 3. And so the alkoxide, the O- anion, is actually relatively stable, which makes alcohols relatively acidic compared to many other compounds. But they're definitely not strong acids at all. They're not in the strong acid realm. So just going through some of these properties that affect acidity, a little bit more review. The first is the ability for a molecule to engage in resonance. So we can directly compare here cyclohexanol to phenol. Cyclohexanol and phenol both attached to a ring, both attached to 6 carbons. The phenol has a pKa that is 8 units lower than that of cyclohexanol. So this means phenol is much, much, much more acidic because the pKa is 8 orders of magnitude lower. And this is partially attributed to the fact that the conjugate base of phenol can undergo resonance. So this oxygen can stabilize the negative charge, but we can push the negative charge down to this carbon through resonance, once again all the way down to this carbon through resonance, and then finally up to this carbon through resonance. So there are a total of 4 atoms that can stabilize the negative charge of the phenol, and that will lead to its increased acidity. Another mode by which we can explore acidity is induction. So induction is the presence of electron withdrawing groups, and so the more electron withdrawing groups that we have, they can, through the electronegativity difference between the chlorine and the carbon, there's a dipole moment in the direction of the carbon. So you could think of these chlorines as hogging electron density, and this dipole moment flows through the sigma bonding framework of the molecule. So some of the negative charge that would build up on the oxygen when it's deprotonated can be stabilized through these chlorines or other halogens that might be attached to the molecule. So comparing ethanol to trichloroethanol, we have a 3.8 pKa difference between the two molecules. Solvation effects also affect acidity. The ability of the molecule to react to be exposed to an additional group. So the more poorly solvated the conjugate base, the less stable it is. And so if we have an O minus here, right, this O minus is because of the steric bulk of the terp-butyl group is going to be, it's going to be really difficult for it to interact with other molecules. So we have a higher pKa. This isn't a huge difference between the two, but it's about 100-fold, right? 2 pKa units, so 100-fold less acidic because of the steric bulk of these two additional methyl groups. And this is kind of a visualization of that. You can see many more solvent molecules will be able to interact with the negatively charged oxygen compared to with the terp-butyl because of that steric bulk. There are a variety of methods that we have to synthesize alcohols. Most of these methods we've already covered, but we'll just do a small review and kind of get them all summarized in one place for your notes. So the substitution reaction, both SN1 and SN2, can be used to synthesize alcohols. If we want to synthesize a primary alcohol, we're going to want to use an SN2 reaction, and an alkyl halide we can use sodium hydroxide, and that will do the trick. And if we want to form a tertiary alcohol, we're going to have to use a different mechanism for this, and that would be an SN1 mechanism. So we could form a tertiary alcohol with the acid catalyzed hydration of alkyl halide. Alcohols can also be synthesized from alkenes. And during chapter 9, we looked at 3 different sets of conditions for addition reactions. So using sulfuric acid, we can attach the alcohol to the more substituted position. Using the oxymercuration demercuration, followed by sodium borohydride, we could also attach it to the more substituted position. And using hydroboration oxidation, we can form the less substituted alcohol, or the anti-Markovnikov product. So here are 3 different methods that we can use, all of which are review to produce alcohols. So today we will look at one new method which we can use to prepare alcohols. And this new method is through the reduction of a carbonyl compound. In order for us to understand this chemistry, we're going to have to talk a little bit about reduction and oxidation. These are reviews from general chemistry, but as they pertain to organic chemistry, there's a few nuances that we need to kind of look at. So when we're talking about oxidation and reduction, what we're really talking about is how many electrons are around the atom, or the formal charge is kind of how the formal charge is the way that we've mathematically kind of assigned this. So when we look at the oxidation and reduction of carbon compounds, what we want to do first is kind of figure out what oxidation state we're in. So let's take a look at methanol. So methanol, we have 3 hydrogens attached to carbon and 1 oxygen attached to the carbon. And so if we wanted to determine the oxidation state of this, we can compare it to its formal charge. So the formal charge, if we treat all of these as covalent bonds and break them homolytically, the formal charge would be 4 electrons. If we treat them as ionic bonds, which we will do for the oxidation state, then we're actually going to have 6 electrons around the carbon, because there's a large electronegativity difference between the carbon and the hydrogen and the carbon and the oxygen. So the carbon attached to the hydrogen, the carbon is going to be sharing more of those electrons, gathering more. So we're going to give the carbon 2 electrons for each hydrogen and only 0 electrons for the oxygen, because the oxygen is more electronegative than the carbon. So if we treat these bond breaks as heterolytic or ionic bonds, then we end up with 6 electrons attached to the carbon. So the oxidation state compared to the formal charge is 4 electrons compared to 6 electrons. And so when we think about the oxidation state of carbon, we really are looking at how many carbon-oxygen bonds. So going from left to right, we have the 5 different structures, each with a different number of oxygens attached to the carbon. So on the left we have methane, carbon attached to 4 hydrogens. In the case of this, all 4 bonds break, each of 2 electrons, and they all go to the carbon if we're going to break them ionically. So this carbon would have an oxidation state of -4. In methanol, we've now created 1 carbon-oxygen bond, so it's -2. And as we add more carbon-oxygen bonds, it's going to go up. So formaldehyde, we have 0. So this has 2 carbon-oxygen bonds. Formic acid, now we have 3 carbon-oxygen bonds, it's 2. And then carbon dioxide has the highest oxidation state of carbon, and this is 4. What we're looking at for the production of alcohols using this method is the going from formaldehyde, or an oxidation state of 0, or a ketone or a carbonyl compound, and reducing that down to an oxidation state of -2, which is where we find our alcohol. So we can convert any carbonyl compound into an alcohol. And this is going to require a reducing agent. So the carbonyl is reduced, and the reducing agent is oxidized. And we're going to be breaking 1 bond. We're going to be breaking a carbon-oxygen pi bond. We're going to be forming 2 new bonds, 2 bonds with hydrogen, one of which is a oxygen-hydrogen bond and one of which is a carbon-hydrogen bond. So we're going to look at 3 different reducing agents that can be used to convert a carbonyl compound into an alcohol. The major difference between the 3 that we're going to look at is the strength. Some of them will also reduce other functional groups. And so we'll start with the least strong, and that's just we'll start with the strongest, which is going to be catalytic hydrogenation. So this is a combination of hydrogen and a transition metal, such as platinum or palladium. And this is going to reduce carbonyls down to alcohols. Unfortunately, it also reduces alkenes down to alkanes. So this will be our strongest. Then we have sodium borohydride, which is going to be our weakest. This will reduce just the aldehyde or ketone to the alcohol. And the mechanism by which this works is nucleophilic attack. So first let's look at the structure of sodium borohydride. We're going to have an ionic pair between the boron with a negative charge on it and the sodium with the positive charge on it. And so this boron has 4 hydrogens attached to it. One of the hydrogens will act as a source of hydride. So that's H minus, hydrogen with 2 electrons on it. So the first step is we're forming a bond between the hydride and the carbon of the carbonyl. Remember, the carbon of the carbonyl has a resonance structure where it has a fully positive charge on it, and it also has a partial positive charge on the carbon due to the electronegativity difference between the carbon and the oxygen. So the first step is nucleophilic attack of the hydride, negative charge on the carbonyl carbon, and then the pi bond breaks, and those 2 electrons from the pi bond move up onto the oxygen. And that gives us an O minus. The second step of the reaction is a proton transfer to form the alcohol. In the case of an unsymmetrical ketone, if we do this reduction, we're going to now form a stereocenter. We go from an sp2 carbon to an sp3 carbon, and this sp3 carbon has 4 different substituents attached, so that's going to be a new stereocenter. And so we would obtain, depending on which side the nucleophile or the hydride attacks, we will obtain the 2 enantiomers of the product. The final reducing agent that we're going to use for the carbonyl compounds is lithium aluminum hydride. This structure is very similar to sodium borohydride. We just have a different counterion and a different metal, and this is often abbreviated LAH. Structurally, these two are very similar. The biggest difference is reactivity. Remember, all 3 of our compounds are going to have different reactivity, and so the ranking is LAH is more reactive than sodium borohydride. So most reactive we have is the hydrogen, then LAH, and then sodium borohydride. And you're going to need to know the difference between these 3 because there will be questions where we have different functional groups in the molecule, and we want to make sure we use the right reagent so that we're only reducing the functional groups we want to reduce. The mechanism here for lithium aluminum hydride you can see is more or less identical to the mechanism for sodium borohydride. We do need to add a proton source after the carbonyl is reduced to protonate the alcohol. So let's look at this molecule. We have in this molecule a ketone and an alkene. If we use sodium borohydride or lithium aluminum hydride, we're going to reduce only the alcohol and the alkene will stay intact. If we use hydrogen and platinum or palladium, the catalytic hydrogenation conditions, we're going to reduce both the carbonyl and the alkene. So this is one example where we would need to, depending on the product we want, figure out which set of reagents is suitable for this transformation. We can also change the reactivity of these 2 reagents by changing the groups that are attached to the central metal. So in these 2 examples, we've replaced the hydrogens with R groups, and depending on what we have attached in these R groups, we can increase the steric bulk of the metal, which will reduce the reactivity of the hydrogen. And we can target specific functional groups to reduce by using this. So we looked at examples where we have ketones and aldehydes, just a carbon-oxygen double bond. But there are some compounds, like carboxylic acids and esters, that have 3 bonds to oxygen. So this is a different oxidation state. Remember, this is the +2 oxidation state, where we have 3 bonds from carbon to oxygen. And using LAH, we're going to be able to reduce the carboxylic acids and esters all the way down to the alcohol. LAH is strong enough to reduce the esters and carboxylic acids. Sodium borohydride is not strong enough. So we've already looked at the difference between catalytic hydrogenation with H2. Now this is the difference between sodium borohydride and LaH. And this is a big difference. If we have a molecule that has a ketone and a carboxylic acid, we can selectively reduce the ketone using sodium borohydride, whereas if we used LaH, it's going to reduce everything. And the mechanism is going to be very similar to the mechanism for LaH reduction of a ketone or aldehyde. First, we have a nucleophilic attack, and the second step is different. We have a loss of the leaving group in the second step instead of a protonation, and this reforms a carbon-oxygen double bond, which can then undergo a second nucleophilic attack before the proton transfer occurs. So this second half of the mechanism is the same mechanism that we saw a few slides earlier. This first half of the mechanism is the biggest difference, with loss of the leaving group step being the largest difference between the two. Generally, methoxide's not a good leaving group, but in this case, it can act as a leaving group because we have a high energy intermediate that will become a stable aldehyde once it leaves. So here are some example problems that we're going to go through during lecture, during the interactive class lecture. But if you want to take a look at some of these problems in advance, here they are for you.